Hi everybody, this is Wemmje, and welcome to my Love VFX course, in which I will talk about the creation of my fantasy short film nöck with Nuke Studio. You can find the link to my short film in the description of this video. In this lesson I will talk about 3D camera tracking in Nuke, and how I tracked one of the creature's clean plates for my fantasy short film nöck. Keep in mind that I'm not a match moving expert. I'm just sharing some of the things that I've learned about 3D camera tracking in Nuke over the last 9 years. Since this is not a course for beginners, I'm assuming that you already know what a 3D camera track is, what parallax is, and that you know when you need a 2D track or a 3D camera track to integrate your 2D or 3D elements into your live action plate. In this lesson, I will talk about a best case 3D camera tracking scenario, in which I have all of the data that I need to get a very good 3D camera track. Whenever you are working on your own project, you can turn it into a best case 3D camera tracking scenario. You can make sure that you get everything you need for a good 3D camera track and that you get a trackable plate, which is exactly what I did for my short film nöck. That best case scenario would include having a plate of a lens distortion grid that matches to the camera settings and the camera setup of your plate, and your shot data like the focal length of the lens that was used for your plate and the film back or sensor size of the camera that your plate was shot with. The information about the codec, resolution, and frame rate of your plate is always available to you as long as you don't delete your plate. I can highly recommend to record a noise profile plate. If you want to know more about this subject, you can check out my video tutorial about denoising with Neat Video for Nuke. I'll leave a link to that tutorial in the description of this video. You can even use a noise profile plate to reduce a fixed noise pattern in your footage. I'll show you how I did that with my footage later in this video. Okay, so in that best case scenario, and before we would start to track anything, we would start with a plate of a lens distortion grid and Nuke's lens distortion node. You need to go through this step to remove the distortion in your plate that is caused by the lens before you start with your 3D camera tracking. Fortunately, Hugo Guerra created an awesome tutorial in which he explains in great detail why you need a lens distortion grid and how to shoot one properly. You can find the link to Hugo's tutorial in the description of this video. Okay, so here we have the lens distortion grid that I shot with the same camera and lens combination and camera settings that I used for all of the clean plates for my CG creature. Here you can see undistorted and redistorted versions of the grid with lens distortion nodes and ST map nodes. The only reason why these undistortions and redistortions are a tiny bit different from the original lens distortion grid is because of the filtering that happens with the distortions of this image. By default, the filter settings of the lens distortion and ST map nodes are set to cubic, which is a filter that blurs the image a bit. I personally prefer to use the Lancos 6 filter setting because it sharpens the image a bit instead of blurring it. If you want to know more about Nuke's filter types, you should check them out in Nuke's online documentation. Let me show you how simple it is to undistort your lens distortion grid. You just need to create a lens distortion node, connect it to your lens distortion grid, open up the lens distortion node's properties, make sure that your lens type is set correctly, which is fine in this case because I've used a spherical and not an anamorphic lens. Then you can go to the Analysis tab, click on Detect, check if the crosses and lines are aligned with your grid, and correct their positions if they are not to get a good result. And then you can click on Solve. The solving process has automatically undistorted the grid, because its output mode is set to undistort by default. Of course, you can also redistort your source after the solving process, by switching the output mode to redistort. In order to save a lot of rendering time, you should use the ST map node instead of the lens distortion node to apply or remove lens distortions in your comp. To render out your ST maps, you need to change the output mode of your lens distortion node to ST map and render them out as 32-bit EXRs. But don't forget to set the channels knob of your right node to all, so you're actually rendering out your forward and backward layers, which let you distort and undistort your footage with the ST map node. If you're not rendering ACES CG EXRs and working in ACES and Nuke, make sure to render out linear EXRs for your ST maps. Of course, you can also shuffle out your forward and backward layers into the red and green channels to export these outputs as separate EXRs. I just prefer to render both layers in one EXR to have the ST maps in one file. Once you have rendered out the forward and backward layers like I have, you can shuffle these UV channels out into RGB space, but the blue channel is actually not being used by the ST map, as you can see in the Shuffle node. Shuffling out the ST map's UV channels is not mandatory, because you can also directly set the UV channels knob of the ST map node to forward if you want to undistort your source, and backward if you want to redistort it. shuffling out the forward and backward UV channels into the red and green channels, and renaming them is just a way for me to make it easier to work with the STMap nodes. So I can just set the UV channels knob to RGB and connect the STMap input to the undistorted STMap if I want to undistort my source, or connect it to the redistort STMap if I want to redistort my source. As you can see here, I'm a huge fan of stamps for Nuke to create instances of my STMaps and most of the plates and assets in my node tree. Stamps is a Nukepedia tool, which you can think of as a postage stamp system on steroids. If you have never heard of it, you should definitely check it out. I'll leave a link to this tool and a review I created about it for Nukepedia in the description of this video. Okay, let's continue with the last step that I usually take before I start the 3D tracking process, which you could call optimizing the plate. In this process, I denoise, color correct, and sharpen the plate to make it easier for the camera tracker to get good auto tracks. Now, if you take a look at the plate, when I gamma the viewer all the way up to 4, you can see the fixed noise pattern that I have already talked about. To reduce this fixed noise pattern, I took this noise profile plate that I recorded with the same camera settings and setup of my plate in complete darkness. Then I used this OCIO CDL transform node to multiply the noise plate down a bit with the slope slider set to 0.5. And then I just merged it with my plate with a from operation, which, as you can see, reduces the fixed noise pattern by a lot. It also changes the color of the plate, which you could try to counteract with another color correction. But if I turn the gamma slider in the viewer back to 1 and toggle the merge node off and on, the color correction that is caused by the reduction of the fixed noise pattern is not really noticeable. Now, right after optimizing the plate, I use a lens distortion node to undistort the plate. And then I can start and create a new camera tracker that needs to be connected to the lens distortion node. Now I can open up the camera tracker's properties and start by setting the focal length to known and 24 and the film back size to 25.34 by 14.25 millimeters, which is the focal length that I used for this plate, and the sensor size of the Ursa Mini Pro. In this case, I can leave the lens distortion knob to be set to no lens distortion because I already undistorted the plate. If there would be something that I would need to mask out, I would create an alpha for that area, connect it to the mask input, and set the ignore knob where it says mask to mask alpha. But that's not necessary in this case. Before I move on to the settings tab, I wanted to mention something about sensor sizes or film back sizes. One thing that is very important to know about that subject is that many cameras, including the one I have used, do not always use the whole sensor for all of the available resolutions they can record in. Let me show you what I mean. My Ursa Mini Pro uses its full sensor size when it's recording in 4.6K. But if I want to record in Full HD in Blackmagic RAW, the camera crops into the sensor. Now, if you want to create a 3D camera track, you need to give the camera tracker in Nuke the correct film back size. 4609 divided by 1920 equals 2.4, and 2593 divided by 1080 also equals 2.4. So if we divide 4609 by 2.4 and 2593 by 2.4, we get from 4.6K to Full HD. That means we only have to divide the height and width of the Ursa Mini Pro's full sensor size by 2.4 to get the cropped sensor size we're looking for, which is 10.55 millimeters by 5.93 millimeters. But keep in mind that the scaling up and down to different resolutions is not always proportional. In this case it is, because both of these resolutions have an aspect ratio of 16:9. Although the calculation of your correct film back size might seem like a very boring fact, it's actually very important to get accurate 3D camera tracks. An awesome online resource that gives you information about the film back sizes, resolutions and codecs of most of the cinema cameras and much more is vfxcamdb.com, which stands for VFX Camera Database. So do check that website out whenever you need some information about specifications of cinema cameras. I'll leave the link to that website in the description of this video. Okay, now I will continue with the Settings tab. In the Settings tab, I usually start with bumping up the number of features and checking the Preview Features box to get instant feedback from any changes I'm making. In this case, I will set the number of features to 600. Increasing the number of features will help in shots that are difficult to solve. So don't shy away from testing out a higher number of features for your plate if you find out that it helps you to get a better 3D camera track. The detection threshold will help you with the positioning of your features. A high value selects prominent points and a lower value will spread tracks out, which can produce a more accurate solve. With the feature separation value, you can force feature tracks to cover the image. You can reduce the feature separation value when you increase your number of features. And by the way, most of the stuff that I'm telling you about these settings is also available to you through the tooltips that you can see when you hover over the knobs with your mouse cursor. I always like to have the Refine Feature Locations box checked, because it helps the features to lock onto local corner points. I usually don't mess with the tracking and solving region unless I have a plate that has a lot of motion blur. In that case, I try to reduce the keyframe spacing value, which can give you a more accurate solve and fast motion sequences. Once I'm done with adjusting the values in the Settings tab, I'll uncheck the Preview Features box, go back to the Camera Tracker tab, and press Track. Once the tracking is done, I can press Solve. And once that is done, I'll try to reduce the error value of my auto tracks in the Auto Tracks tab. Here you can get a very good look at the accuracy of your 3D camera track. To get a better look at the track curves in the user interface, you can select the name of the curves you want to see, let your mouse cursor hover over this field, and press F. You can look at curves like the minimum, average, and maximum error per frame. Of course, the idea behind all of this is to get the tracking error as low as possible to get a better camera solve, to have many good auto tracks and getting as close to having no bad auto tracks as possible. With these 3 sliders in the bottom, you can control the rejection of your auto tracks. You can choose the minimum length for them. With the min length slider, you can reduce the maximum average tracking error with the max track error slider, and you can reduce the maximum error of your tracks with your max error slider. Once you have adjusted these settings, you can choose to delete the unsolved tracks which are invalid, delete the rejected auto tracks that exceed the track thresholds, or delete all of the auto tracks if you want to start over again. Once you are happy with the result, you can go back to the Camera Tracker tab, press Update Solve, and press OK. There might still be a few bad auto tracks left, but I will leave that as it is for now, because the error value that I have for a 4.6K plate is actually pretty good. When you're creating a 3D camera track for an HD plate, it is best to not get a tracking error value over 1. Finally, I can select a few solved auto tracks on the floor with the lasso selection tool, right-click, go to ground plane, and press Set to Selected. That sets the selected auto tracks to Nuke's ground plane. Now, if I create a camera, double-click on it, and look at it in the 3D viewport, you can see the camera and a small point cloud that represents the auto tracks in 3D space. To check if the 3D camera track is accurate, I have prepared a small scene with a card and a checkerboard on the floor. So if I look at this merge node and press play, you can clearly see that the camera track works like a charm. It is an industry standard workflow to only add the distortion of your plate to your CG elements, so they distort the same way your background plate does, and leave the plate as it is recorded with the lens distortion. Keep in mind that you might need to adjust the overscan settings in the scanline render or in your CG renders if the lens distortion you're applying to your output is cropping it at the same time. For every creature shot in this short film that I had to create a 3D camera track for, I created scene geos with Nuke's point cloud generator, and then I exported the 3D cameras and the scene geos with right geo nodes as Alembic files. Here is how I created this geometry of my scene with the point cloud generator. After creating a point cloud generator node, I connected the source input to the undistorted plate and the camera input to my tracked camera. If you can, you should use an undistorted plate and a 3D camera that was created with that undistorted plate, because that will give you a more accurate result. If you have something in your plate that you need to create a mask for, you need to connect that mask to the mask input, open the point cloud generator's properties, and set the Ignore Mask drop-down menu to Mask Alpha. But I didn't need to do that in this case. After the connections were all set up the right way, I changed the frame spacing value to 5 and pressed Add All. With this step, you're creating the keyframes that the point cloud generator will use to create the point cloud. There should be enough keyframes so that the point cloud generator can understand the depth of your scene from one keyframe to the next, just like in a photogrammetry scan. So after I have set the keyframes, I press this button that says Track Points, and right after the tracking was done, I selected all of the points in the viewer with vertex selection enabled and the lasso selection tool, created a group on the point cloud generator's group tab, selected that group, and baked that selected group to a mesh. Creating such a mesh for your scene with the point cloud generator is very easy, but it can help you a lot during your work in 3D and compositing. Alright, that was it for this lesson. In the next lesson, I will start to walk you through some of the comps of my short film. Feel free to post any questions you have about my work in the comments, and I'll do my best to answer all of your questions. If you want to see more of these videos, don't forget to subscribe. Again, this is Lars Wemmje. Thank you for watching, and goodbye everybody.